topic for today's lecture is called audio, and I will try to follow you through basic principles about sound and then basic principles about digitalization of sound, and then in practical part of this lecture I will try to show you how can you handle sound and edit it in personal computer using free open source tools. And so, what is sound? Sound in general are vibrations that travel through the air or some other medium, and there are differences how theorists look like on any vibration and sound and what they call as a sound, but in general, if it goes through air or water, which is easier to move, then it's considered sound. If it goes through how it's called, solid materials, it may be called just a vibration, but in general these are disturbances in some medium. And particularly in sound, what is important is that in solid materials like glass and metal, there may be different kind of vibrations where traveling of this vibration is going in the same direction or in different direction. For example, if you know something about earthquakes, which are also vibrations after shifts of large more mass. So, okay, let's make it nicer. So this would be earth, and here is quake. And earth may be moving up and down or left and right, and then these disturbances might travel around the surface of the earth. But through the earth also this up and down movement may travel as a compression waves, where the solid material is a little bit compressed and then decompressed, compressed, decompressed, compressed, decompressed. So there is difference if this material is moving just left and right, up and down, but wave actually is following in orthogonal direction, or wave actually is going in the same direction, forward and backward, while wave is going forward. And particularly in sound for air, these waves are going in the same direction or opposite direction as they travel through the air. So these are compression or decompression waves going through this medium. And what is important things about sound wave properties? First, its amplitude, or how powerful it is. Then frequency. It may consist of many frequencies. I will try to show you later in demonstration. And these many frequencies together may make timbre for particular sound. And then when you have some wave which started coming from somewhere and then finished, so it's not going continuously forever, then of course phase is also important for continuous waves as well, because you can use phase to triangulate more precisely from which place this wave is actually coming. And so that's very important thing for any kind of waves as well. And amplitude in general is measured in decibels, which is logarithmic scale, and that means any logarithmic scale is like this. You see something like, for exponential growth, here is 0, 1, 10, 100, then 1000, then 10,000, and hopefully you got idea now. So you see that gradually this scale is compressed more and more. So if you look linear difference between these scales for each particular step, actual presentation of amplitude, what they represent in this case, is 10 times bigger. And in opposite directions, that would be -1, -10, -100, or no, 1 divided by 1, or 10, then 1 divided by 100, then 1 divided by 1000, 1 divided by 10,000. That would be proper logarithmic scale. So on this direction, when you go in negative scales, actually it is stretched. So each particular size of step represents 10 times less difference than previously. And such scale is very important and useful when you need to compare very huge differences between values. Otherwise you always run out of paper and area. And so this logarithm may be, as a base for this logarithm, may be used different numbers, natural logarithm, decimal logarithm, power of 2 also, but idea here is the same, that for each particular discrete step they represent either n times more or n times less than in previous step. And particularly for sound, not decimal logarithms are used, or logarithms with base 10, so that means 10 times more something. But particularly for sound, for various reasons, it has also multiplier here as a constant to make these steps more easy to divide. And then, because of historical development, how acoustics and physics developed, there may be confusing things what one particular step for these logarithms or decibels represents. And in general, in physics, usually these decibels, by the way, it is always relative number, so you see something observed and you divide it by reference. And for example, for radio electronics, this reference usually is 250 milliwatts or 1/4 of a watt, but maybe also different reference as well. And so for sound, usually when you measure things, you measure power. For example, for electronical devices, electric devices, etc. And probably you remember from secondary school of physics that power is, for example, for electrical devices is voltage times amperage, or amps and volts, or spriegums. Yeah, voltage and amperage. So, and these in electronics, usually using similar approach for acoustics as for electronics, you may use sound power as this representative scale of power, how powerful it is. Then, because how power is related to amplitude of these sound waves, then, for example, for 10 decibels of difference, power changes 10 times. So that would be, as I showed you here, in this scale. For each of these ones times, it's 10 times more. And approximately for 3 decibels, it means approximately 2 times more. But they also may measure sound pressure, which means how big pressure in millipascals or micropascals these sound waves going forward, backward are making. And then this scale is twice as lower, and that means that to get pressure difference of 10 times, you need to get 20 decibels, not just 10 decibels. And to be more precise, they may say that in this case decibels are measured for sound intensity level or sound power, or decibels for sound pressure, which is in according to micropascals, 20 micropascals, not millipascals. For example, for this, and this of course is quite a difference, because in one case it is, for example, when you switch and see difference of 30 decibels, in one case it may be approximately 20 times, in another case it may be 100 times, and 20 times and 100 times of course is a little bit of difference. And because of that, when you measure sound in decibels, the precision is something like in kilobytes, megabytes, where computer scientists wrongly decided that 2 in power of 10, which is 1024, is approximately as 10 in power of 3, which is precisely 1000. And then when you talk about kilobytes or whatever, you know that there may be some difference, 1 point times in one direction and 1.5 times in other direction. Because of these differences, what do they mean? Of course, if you follow standards precisely, they should be kibibytes and they should be kilobytes. And similarly, if you follow standards precisely, you should say, do you measure sound power or sound pressure, because otherwise you may again get differences approximately a few times, depending on how you look on this logarithmic scale of decibels. But unfortunately here I think this standardization is not so well done yet, so there may be some confusion around, for example, how many decibels represent difference of 10 times, either 10 decibels or 20 decibels. And so here is a scale which talks about pressure ratio, which means 10 decibels means 10 times difference. And so minimum audible sound is approximately 1 decibel, calculating it for sound pressure, not for power of these sound waves. Soft whisper is 10 decibels, quiet office 100 decibels, average conversation 1000 decibels. Yeah, not, sorry, where's decibels? Here. So 0, 20, 40, you see, 10 times of difference are 20 decibels in scale here. So 0 decibels, 20, 40, 60. So point result is approximately 440 decibels. And above that you actually may seriously and irreversibly damage your hearing if you are in an environment where this sound pressure level is higher. So another important part for sound is frequency or pitch, and this is how frequently these sound waves go forward and backward from high pressure to low pressure and back. And here, no any confusion, frequency is calculated in hertz. Why usually we calculate frequency, not length of the wave? Because you know that in any time, for example, when we talk about speed of light, we can say that from which when they start. So frequency is per second. This is velocity calculated by lengths. Lengths lambda calculated by velocity. So this is meters in second, but this should be per second, and that means it's completely opposite. It means v calculated by lambda. So here I don't know this very precisely, but if you know measures, here as a former physicist I apply this rule of measurements, and if frequency is something against seconds, I know that for other calculations my final calculation also should be against seconds. So this one is right. Yeah, so why they do not measure lengths of sound waves? Because, for example, speed of light is constant, so there is very strong and exact relation for one and another. But even for speed of light is not constant, because for different materials it may be different. But for sound waves, this speed of sound waves is very different. For example, it's approximately 330 meters per second in air. It may be few kilometers per second in solid materials and in water. So this means that in water these sound waves are much shorter than in air, and therefore what they usually measure is these vibrations, how they go forward, backward, because this is less changing thing. And so they measure it in vibrations per second or hertz. So measurement of hertz is 1 divided by second, or 440 per second. And so for harmonic waves, which you see as a sinusoid on the graph, there is only one parameter besides amplitude, this amplitude and period, nothing else, because there is no anything which describes this wave, how it is happening. But then, of course, for these waves, they may sum, and then they may either make the total value bigger or smaller, which is this sound interference, and then you can get some resulting wave. For example, here we have approximately two different sinusoidal waves or harmonic waves, and we get the total wave something like this. And then, of course, we cannot describe it only by amplitude and only by one particular frequency, but it actually is sum of different frequencies and different amplitudes together. So here what helps you is if you know something about Fourier transformations. And I think in English Fourier is written Fourier. And Fourier initially developed transformations using integrals. This is continuous transformations, but today usually we use fast digital Fourier transformations, FDFT. So, and what does it mean? It means that you can look on some wave here, and in these analog integral transformations you start from minus infinity and you end up with plus infinity. And so here is time and amplitude, and then you can transform this infinite graph into finite graph, where amplitude is shown against time or reverse of time, and that is frequency. And for this particular sinusoidal wave we see that there is only one single amplitude, let's say somewhere here. I don't know, if here is 1 second, then here will be 1 hertz, or 1 against second of amplitude. And so you can transform from such a long continuous wave movement into one very discrete amplitude and say this. And we have some sum of waves, like one little bit longer, another little bit faster. Then in sum they will be something like this. But if we will transform it back against time and see what amplitudes we have, we will see there is one lower frequency, that would be this red one, and one blue frequency. And similarly, you can do this using not integrals but discrete points. Only difference is that for integrals you need to start from minus infinity to plus infinity, or you add so-called window function, and window function cuts somewhere this signal in time, or fades in and fades out. And so that would be amplitude for Windows function. It increases amplitude somewhere here, it may be prolonged some plateau here and decreases. And this is usually what is used for fast discrete Fourier transformations, and because of that you never can see frequency absolutely precise as one infinitely small bar here, but you will see that frequency is somewhere around here and somewhere around here. So on this imprecision is because of this window function, because you never know what is happening. This function may be very nice here, sinusoidal, but then after here it may be something completely wrong. And you never know what is here, but you know that so far from here to here definitely there were no different frequencies in this particular signal or this sound wave than this particular frequency and that particular frequency. And again, I will try to show you how it looks in practice in some of editing tools as well. So now about, we will not go into details about biology here, but what is important here to understand how we actually hear these things and what are important aspects about this. So here is very simplified drawing of human air. So here sound waves come in, then they stop here in this membrane, air drum. Then these sound waves are transmitted through other mechanism, kāpslītis in Latvian, where āmuriņš laktiņa, something like this. So it goes through solid material here, then it starts vibrating fluid, it's mostly water, in this inner air, and then here we have very many, something like hammer and anvil in English. And then here it makes vibrations into this water, and then here are very small spores of this inner air which also are fluctuating according to these vibration movements of this water or fluid. And what is important here is that everything together here is non-linear system. What means non-linear system? Linear system is following system. You have some amplifier or anything else, and here is, let's say, input value, and here is output value. And for any linear system, output is depending on input absolutely linearly. So if you increase input few times plus x, so this is something like, let's say, I do not know, 1.5x, and this would be, let's say, 0.5 plus 0.5 of x. So if this is linear system, then there is very precise correlation how one amplitude is changing about other. So this is linear. And in most of amplifiers, of course, you try to make them as linear as possible because they introduce other things. But if you have some non-linear system like this, then you have this input and output changing non-linearly, and that means that if for input you have, let's say, very nice harmonic sinusoidal signal here coming like this, then for output you will have not precise sinusoidal signal, you will have something like this with some cutoff. And if it's not precisely sinusoidal signal anymore, if you will look on Fourier transformations here, you will see that here is just one precise one frequency, which is frequency of this sinusoidal signal. But because here you do not have sinusoidal signal anymore, you will have maybe 2, maybe 3 other frequencies with smaller amplitudes. So this means when we are hearing sinusoidal or absolutely harmonic signal, what we are actually we hear other notes as well, because our sound system is not absolutely linear. And of course, with our brain, we compensate for it. So if you see or if you hear signal with like 3 harmonics like this, then you assume what you actually are hearing is very clear sinusoidal signal. But sometimes you do not compensate for it, and that means you actually hear ghost notes or ghost signals which are not there, but which are happening just because of our hearing system is not absolutely linear. And what is good about this non-linearity is that we have a little bit easier life to compare pitch of signals, because when we compare pitch of signals, we actually are listening not this basic pitch rate, but differences from signal to signal for these ghost frequencies as well. So it's good thing. And also because of this non-linearity, we can hear starting with very silent and quiet noises till to very big and loud noises, because of this non-linearity mostly coming from this hammer and anvil system. Because if this noise is too loud, we have empty air here, so we do not transmit all large vibrations directly here, so we do not damage our ears with much louder noises than if our hearing would be absolutely linear. So, and then what do we hear? Here is comparison of graphs, what is minimum frequency and maximum frequency, what I hear different kind of animals. And in most of cases, larger animals hear lower notes or signals, and small animals hear higher frequencies. But particularly for aquatic animals like whales and dolphins, they actually hear quite a lot of what we consider ultrasound, because they use ultrasound like bats for echolocation, or how it's called, echolocation. So, and very good human might hear approximately from 20 Hz to 20 kHz, but average human usually start hearing something from 30 Hz to maybe 16 kHz, and with age this upper bound becomes lower and lower, and at a very old age you are happy if you hear only 8 kHz. But again, about these lower tones, for example, if you know something about music, you know that particularly for organs, the lowest note what they are using is 16 Hz. But if normal human might hear only 20 Hz, but average human may be starting with 30 Hz, how can we actually hear such very low note? And answer is we do not hear it. We may feel it with our stomach and body, and then we can use our brains to consider this as well. But what is happening in our air system is following. So here is amplitude and here is frequency, that means hertz or something against second. And so here is very low note, 16 Hz. We do not hear this because our ears are not built for that. But because of this non-linearity of the system, even if these 16 Hz are absolutely sinusoidal and harmonical signal inside our air, what is happening is these 16 Hz which we do not actually hear, but our internal air system adds some amplitudes here of higher frequencies, like first harmonic would be 32 Hz, pēc tam 3 reiz 16 ir cik 68 Hz and maybe more. And starting from here, we actually hear this. And if our brain receives signal that there is frequency with 32 Hz with following amplitude, there is frequency with 48 Hz with following amplitude, and let's say 4 reiz 16, 64 Hz amplitude here, then with our brain, including our stomach feelings, we see, okay, this is 16 Hz signal coming from this big pipe organ. So, and here this non-linearity helps again for us, because with the deducting method of our brain, we can actually feel much lower frequencies than our indicators, not indicators, but receptors can actually receive as actual signals. And so here we see what is so-called dynamic range of human air. Here we see graph of frequencies starting with 20 Hz till to 20 kHz, and as you see here also this is logarithmic graph where values grow exponentially or in geometric progression, if you do not know what exponent is. And here we have these noises starting from 0 decibels, and here they are very precise. They are talking about sound pressure level, not about power level. That means 20 decibels is 10 times difference. And so here is Pine threshold, and here is what we can hear. And approximately around 2 kHz, 3 kHz, we hear the most. And then we gradually hear worse and worse and worse going to lower frequencies, and we gradually hear less and less in higher frequencies here. And this is this default range, what we hear and what we listen like in speech and music, in window for frequencies and in window for amplitudes or sound pressure, how powerful it is. And here it shows also this in more details, but yeah. So now about this timbre or pitch. So different kind of signals may have the basic harmonic or F0 for frequency of basic one, and then it may consist of much bigger harmonics, which makes this signal somewhat different. And here we see amplitudes in time, and here we see amplitudes divided by time, or frequencies. And if you do not remember much about this particular lecture, but if you want to remember something about Fourier transformations, remember that as sharper signal is here on amplitude during time, as more harmonics it will have in this frequency scale. So if signal is very smooth during time, for example, you have something like this, then, so this is amplitude during time, then in frequency window it will be some basic harmonic here and maybe very small upper ones, because it's not absolutely sinusoidal. But if you have signal with very sharp edges, like so here, and if this saw is with infinitely sharp edges, so this is time and this is amplitude, then in harmonic scale, this means 1 divided by time and 1 divided by time, it will have infinite amount of harmonics here, because to make infinitely sharp edges here for signal, you have to add infinitely many sinusoids here together to make these sharp edges. So it's very simple rule of thumb. Every time you see something sharp, that means it has many harmonics here on the scales, and the most sharp signal is following just one peak here during time. When I studied radio electronics in university, we called these signals Asakas. Does anybody know how Asaka is in English? Fishbone? No, even just one word. So fishbones. Fishbones are very sharp signals which may even damage your amplifier and your sound system, because such fishbones are with very many high-end harmonics. So now a little bit about other things about hearing, about phase, and about how we distinguish source of something. For example, here is our two ears for our human, and here some fishbone signal is happening, so that means nothing is happening, and blip is something like this, and then of course it travels through the air, and we get this blip here with some, of course, decreased amount, because it goes in every direction. Maybe it may have also some directionality, and we see that this blip here comes to our ear earlier than this blip here in other air. And our brain actually can calculate this difference and triangulate this, that if there is so much amount of time coming from one blip here and coming to one blip here in our air, then this should be coming from this end. And if there is some other fishbone signal coming from other end, and we hear this little bit earlier in this air and little bit later in that air, again, our brain can do triangulation and calculate that this signal is coming from that one. So that's about sudden changes in things. What is if it is just continuously sinusoidal wave? So we will feel that there is phase difference between one air and another, but because it goes continuously, we may not be absolutely sure where it is, because it may be also coming from absolutely opposite end here, because it goes continuously. So what do you do here? You can see how cats do this. They rotate their head forward and backward for two things. First, for visual perception, and second, for hearing perception. So if you start moving your ears here, you see this phase difference between these signals coming from here and here, and if you rotate your head, you may distinguish these two opposite ends. Is it coming from here or is it coming from here? Because then you will see these phase shift differences. And similar thing is also used for radio astronomy, where they use phase differences between signals to differ and distinguish from which particular positions they are coming. So that's one thing. Another thing is that if we go into more details here and look how our head is looking and how our ears are looking, so from front end we hear much better than from back end, because our ears are made more or less as locators to locate something from this perspective. And also, not only phase is different, but here we listen much more direct signal if it's coming from that end, but here some of signal is actually filtered and going around our head here in that. So here we hear more clear signal, and here we see softer signal where higher frequencies are lost. And if signal is coming from absolute opposite end, so how you can see difference that signal is coming from here and not come here if it goes all the time like sinusoidal signal for forever. So difference here is that our ears are working as locators and filters, that if it goes from the front end, it has more crisp and clear notes or higher frequencies, but here is lower frequencies. And I will try to demonstrate you it with following. So, simple question: did this helicopter, when it was in front of you, move it from left to right or from right to left? For me, I think it was from left to right, but maybe somewhere these channels are mixed up for Zoom session. So that's about these additional things. For example, what we have learned with our brains to understand where this sound comes from, and is this facing us forward or facing backward. So now about digitalization. How do we digitalize this sound? First, we need microphone or device which converts these pressure waves going forward and backward into electricity. And there are many different kind of microphones, but leading de facto standards are so-called dynamic phones and capacitor phones. Where is difference? In general, these dynamic phones are something like your sound system in reverse. It has permanent magnet, it has membrane, to membrane is attached coil, and if you add electricity to the coil, you generate inductive forces, and this membrane goes forward and backward, and absolute opposite. If you change this membrane with coil forward backward, it generates weak electricity, which you can amplify and use. And the bad thing about these are that they are a little bit more massive, more expensive, and more prone to external vibrations. And therefore, capacitor microphones are also used where they use condensator plates, which changes this capacity of this condenser between these plates, and it is cheaper, it can get higher frequencies, it's not so massive. Only problem is that for these capacitor microphones you need additional electricity as external power for them. So and then you get changing electricity, and if system is linear, and we always try to achieve as much linearity as possible in these sound systems, then what is change either in volts or amps inside this coil actually represents what was differences in sound pressures here in air. And what do we do then? We convert this continuous signal into numbers. And to convert them into numbers, in computers they use so-called analog to digital and digital to analog converters. So how do they work? They make samples, continuous samples of this changing electricity. In most cases it is voltage, but sometimes you may be using amperage. But so there are some changes here, and you check how big this signal is, and for this how big you just give number to it. And in most of cases these analog digital converters work in the following way. They use condensers, capacitors. So if here is so big signal and you add capacitor here, then its voltage, so here is our input, and we make some resistor here, capacitor, and make it, let's say, to the ground. What means to the ground? This means somewhere to the ground there is also another part of loop going here in input. And when we add this input, condenser collects this electricity and its voltage. So here, if your input is already high, through this resistor, this will increase only gradually. And if it will be higher, it will increase faster. If it will be lower, it will increase slower. Again, if this capacitor is not full and it do not increase this voltage anymore, it is linear system. And that means that somewhere here, depending on how high this input is, after some time, this voltage on this place on condenser will be either a little bit higher or lower. And then what they do, they switch to other thing, and then they check how much time it took to go to zero back again. And here it is just a timer. So for input, if we now look only on this graph, when this condenser is charged, it may for some time increase its voltage either slower or faster, depending on how high this input was. And here it does it, let's say, for 10 milliseconds. And then for 10 milliseconds it always is discharged through the same amount of resistance, so it is always parallel here and linear. And then we in computers, and that's how most of analog digital converters work. It checks, for example, that here it is 10 milliseconds to discharge, here 15, here let's say 20, here 30, here 50 milliseconds to discharge. Why it does forward and backward? Because with this thing, if something changes in condenser, nothing else changes, because if it becomes older and its capacitance is lower, it will probably start charging faster, but it will discharge also faster. This means if something changes in this condenser, nothing else will change, because then discharge also will be faster, and you will always get, for example, for this amount of signal, 10 milliseconds discharge time. And then, so this time is used as a number to say how big this signal was. And again, there is always some higher limit how you can charge and discharge this condenser, so it will switch to non-linear system. If your input will be much bigger than this, your output will say that signal is not bigger than that, because it cannot measure larger signals than that, so your system will be saturated. So here, because it needs some time to charge and discharge, and what actually is happening, they do not check voltage directly, but they just count time. They regularly charge this microphone using signal and discharge this microphone using other resistor with known resistance, and then these numbers are put into computer. And if we go forward, for example, how we change numbers to signal back, again, depending on these numbers, they have another capacitor here, which, depending on number, either will be charging or discharging faster or slower. So it is something like this, like here you have array of resistors, and their resistance is changing logarithmically. And here are your number, and here is, let's say, plus 5 volts, and here is 0 volts. And then there is another resistance here as output, but we will just put everything here together, and this is out. And then you just add 1, 1, 1, 1, 1. This means add voltage to this resistor here, add voltage here, so it will be higher, and it will charge this capacitor faster. If it here will be 0, 0, 0, 0, this will be disconnected, and this voltage here will be much slower, and this capacitor will be charging much slower, and so you will get much lower signal here. And so there may be different options, but when I was studying radio electronics, in most of cases this was produced with array of resistors. And then, depending on this number, you charge and discharge this capacitor, and then you need to filter it out, and you get numbers back into changed electricity, and then you add this speaker here, which changes changed electricity into sound waves back, and you get numbers into sound back again. So, and this speaker is like dynamic microphone, but opposite one you have permanent magnet, you have membrane with coil here, and depending on what kind of power you have, volts or amps here in this coil, it moves either forward and backward, and you get different sounds out of it. And in most of computers today, of course, and specialized systems, you have both digital analog and analog digital converters together, so you can convert analog signal into digital one, then you can process it like just numbers, and then you convert digits to analog signal back again just to hear it like a sound. So now about these things, like how we actually make these samples. So depending on how frequently and how precisely we will make these samples, our numbers will represent this actual signal either better or worse. And what is important here? First thing is that you always need to measure it frequently enough. Because if we have very nice sinusoidal signal, so it has only one harmonic here, and we will make samples out of it here with the same rate as the sinusoid here, then we actually will not get any output at all. We will get the same value here, the same value here, the same value here, the same value here. That means no any sinusoid or changes at all. So that means it just shift from zero, but no any vibrations. And if we will calculate it not frequently enough, we actually may get this frequency 2 times lower than we actually want, because here this red signal is green signal is actual one what we measured, but because we measured it not frequently enough, we got high value here, low here, high value here, low. And when we approximate it, we see that rate of this recovered signal actually is lower than original one. And so this Nyquist theorem says that with some tricks, because your system should be ideal then, you can recover only half of frequencies from your sampling rate. So if your sampling rate is 8 Hz, then maximum signal rate what you can actually describe is these samples is 4 Hz. If it's 8 kHz, then 4 kHz. If it's 22 kHz, then 11 kHz. But in real system, it is even little less than that because of filtering problems, etc. So to be sure, usually your sampling rate should be 2.5 times higher than you actually use as a maximum frequency of your signal. So, and then you make different kind of measurements of the signal. So here it shows how regularly you did it. This is called your sample rate. And here are how precisely, with how many digits, you digitized this actual value. Of course, it changes continuously, because, of course, it doesn't change absolutely continuously. Each particular electron has its minimum charge, and either you get 1 electron more or 1 electron less. But if you know something about Avogadro number, usually there are billions of electrons involved in actual signals that we are making here, and therefore with that approximation we don't need to count this digitized 1 more or 1 less electron at all. But when we use some very low power electronics, where number of flowing electrons is actually pretty small, then we can actually see that also this level here, if we are using electricity, not light, and for light of course we also have photons, then of course we may see that it is actually changing with some steps. So and then we approximate it, and depending on how precise numbers are and how good this sampling rate is, we approximate this original signal back with higher or lower quality. How can you get higher quality? First, you need to do this sampling more frequently. That is increasing your sampling rate. And second, you need to increase your levels of numbers here, what number you assign for each particular level. And so sample rate should be at least 2 times higher than your maximum frequency of measured signal. And standard sample rate, for example, is 41.5 kilohertz or 48 kilohertz. This is good enough because most of humans do not hear anything higher than 16 kilohertz. And then you need to assign more or less precise numbers here. This is called bit depth. And for computers, this bit depth of course is power of 8, so you can use either 8 bits, and that means you can represent 255 different values, or 2 in power of 8, or 16 bits, or 32 bits. And for example, for higher-end systems here, you may actually use 32 bits, but not as an integer number, but as a floating point number. So it means if you need to distinguish between very large and very low signals, you can actually move your floating point around to use approximately the same precision for very large signals and very small signals. And particularly for this bit range, it also has so-called dynamic range. When I told you what we can hear as a minimum signal and what we can endure as a maximum signal without breaking our ears, it is our dynamic range. So we can hear something like, in ideal, let's say 0 decibels, in practice starting with 10 decibels for pressure, and then up to, let's say, 120 decibels as a higher level. And that is dynamic pressure, dynamic range, what our hearing system may endure without breaking. And similarly for digitalization, for these numbers here, these numbers represents what is minimum amount of signal and maximum amount of signal what you can describe. And as more numbers here you have, as bigger dynamic range for your system will have. So smaller numbers, this means there is always cut-off value where you can't distinguish between low-end signal and noise in system, and in high-end here you can't distinguish with this signal and any signal higher than that. And then when you do this sampling regularly with some numbers, you get total bitrate, which is usually shown for different kind of media. They may say what sampling rate is and what is these precise numbers, but for example, when you download something as a stream from internet, actually this means you need to multiply number of samples per second with bit depths per particular sampling to get actual bitrate for this particular digitalization. And sound quality, of course, is depending on your analog part of system. And for like personal computers, then you cannot get absolutely fine quality just because this analog part of your system is not good enough. But then when you are dealing with numbers, then quality is presented by how much samples do you have and what is your resolution for these numbers. So, now about audio data formats. When you do these samples, you write down these numbers and you just can write it as an array of numbers and say that each number should be converted back to the signal, let's say 22,000 times per second, and then actual numbers are following, and then you get something like uncompressed digital format, and leading format for this is WAV format coming from Windows, but it's used everywhere. It is actually de facto standard besides Mac computers where IF is used for Mac files. So it represents these values just as there are some header part which describes what sampling rate is and what precision is for these numbers, and after that there is just stream of numbers which represents your sound. And depending on this sampling rate, it is approximately 10 megabytes per minute, and so it is quite a lot. What can you do if you want to store them? You can use compression for these numbers, and you can compress it in two different ways. One is like zip archive, which is lossless compression. You just remove redundancy out of these numbers and you compress it like zip archive, and these are called lossless compressors, and usually you talk about so-called codec, and codec is actually acronym from compressor and decompressor, because first when you get your digital data and you compress it and you save it in compressed format, and when you want to replace this data back, you need to decompress. And therefore you have some library which allows you first to compress it and then decompress it, and in general it's called codec. So that's what these codecs means. And what are these lossless codecs? As a leading standard for lossless data is format called FLAC, from Free Lossless Audio Codec, which is used for personal computers, and of course Apple always have something their own, which they try to market as better, like lossless audio codecs and some other things. But de facto standard for modern systems is FLAC format, and because it's lossless, you can compress it approximately 2 times. It of course depends on the changes of your signal, like compressing large bitmap which has only white color in it will be much easier than compressing bitmap which has quite complicated colored image inside it. So, but for standard sound, you may make it approximately 2.5 times smaller than uncompressed one. And then there are number of different kind of lousy codecs which actually work like JPEG images. That means they actually lose some information, but because of that we are not very worried about this, because perceived feeling is not so bad. So how do they work? We will talk about lousy codecs also for images, but in general, for example, for image, we have something complicated written there, and then something is quite dark here. And for loosey image compressions, what they do is that something which is pretty dark, they make absolutely black. And for example, if you look on compressed movies, you will see that all these shades are without any details if it's compressed with quite large compression rate, because the approach is that usually you pay attention to bright details and you do not pay attention to these ones, because usually important things happen into light. And similarly, they do this for sound. And here I hope you will understand this picture, because what is happening here, when you listen to some complicated music, there are many concurrent tracks with different sound spectrum and frequencies. Like you have some bass beat somewhere here, then just some organ here, guitar and other things. And of course it is all happening concurrently, and all these waves are summed up and they make some specific amplitude which you can recover back into initial these tracks and frequencies. And thing here is that because our hearing system is non-linear, if we have some very strong bass beat coming into our ear, then our ear is overloaded with this particular strong and loud and low volume of signal. We actually can't hear anything else which is quieter and with higher frequencies. And when they compress with this loosey codecs, they disassemble or they convert actual amplitude from time back to different frequencies. So it comes like this. So here we have some superposition of this amplitude during time. I need to write it more carefully. And then what is converted? It is converted in different amplitudes for different frequencies for each particular time. And so frequency is here, and amplitude or loudness is with darkness. And what they filter out is, they filter out only and compress it what is the loudest frequency during this particular time, and everything else is just skipped. And we get completely different signal where many things are actually lost here, but because of our non-ideal hearing system, so these frequencies are lost, these frequencies are lost. It doesn't sound very bad for us, because we can't distinguish and hear these things if there is another signal very loud around time somewhere here. So that's what this graph represents. So it filters out and represents only that part of signal which is the loudest one in particular frequency spectrum there. And so we get out of this codec much more simplified signal, which even though it hides and has lost quite a lot of information, it doesn't sound as bad as you may think. And so what are, I think I had, so in old systems, leading lossless format was MP3, and today you can use, for example, open group audio signal or OGA and there are some other ones. So MP3, till few years ago, most of us used it illegally, because to use MP3 format, we had to pay royalties for these inventors who invented this particular compression signal, but nobody of us paid these royalties, so most of us used this MP3 format illegally. And because of that, this OGA, or Open Group Audio, was invented as an analog, but it didn't took off as a very popular one, because patent term for MP3 files, if you are curious, you can search by yourself when it ended up. So this royalty or patent money ended up for MP3 files, and because of that, MP3s are still probably the most widely used ones. And so then, in most of cases, if you do not care about very high precision, for example, you listen your music in noisy places like offices and on street, etc. In most of cases, everybody is listening loosed codecs like MP3, and I think that, for example, if you are listening on Spotify, I think that Spotify also actually provides you signal where some information is actually lost. And then there are CD format, which is not so popular anymore, while streaming services are popular. But in general, it uses 44.1 kilohertz as a sampling rate, 16 bits as a resolution rate for number, and so this is CD quality. And it is uncompressed format, so that means like WAV format, only for CD they add also error correction. For example, if your CD doesn't read very well, so it has some redundancy there for error corrections, that if only some parts are not readable, then this signal can be fully recovered. And then how you edit these digitized sounds? You can edit sounds in two different ways. First, you can use your analog signal and mix it together in your mixer, like from actual recorded sound of your voice, of your systems, etc. So what is good about such thing is that first, this digitization is not rocket science anymore. Anybody who has microphone can do it. Only thing is that many of business-oriented computers do not have good microphones anymore. So one of things why I couldn't do this presentation previously is that my sound system for computer is quite complicated. Any laptop usually has built-in microphone, and it is good enough for conversations, sometimes not good enough even for conversations, and therefore usually if you want to do better quality you need external one. And in old times I have Dell Studio, and for Dell Studio it has microphone input, so I had different microphone, both mic input and phone output. So, but then later I switched to different computer which had phone output, but no good microphone input, so I added USB microphone. That's one complexity. Then I switched to different computer which even don't have phone output for headphones. So I added another USB card with microphone input and phone output. But because I already switched to a dedicated USB phone, then I didn't want to get another microphone just for that. So that means for my computer I have two different microphones, one built-in, actually three, one built-in, one for dedicated USB microphone, and one actually not used for external USB card, where I use only for phone output. And sometimes settings got confused and I can't just find out what is wrong here between these three microphones. Usually it happens once, twice a year, and I only forget how this actual USB microphone is called, how exactly this USB card is called, etc. etc. So if you have a messy system, then of course your life becomes quite more complicated. That may be your problem. That microphone is actually not good enough. You may need a dedicated one, etc. And then you can use a standard called MIDI, and MIDI comes from musical instrument digital interface. And MIDI is like vector graphic for pictures. You may describe everything just as a pixels. And because sound is one-dimensional just during time, of course you represent it as like a pixel here, pixel here, pixel here for each particular thing. Of course you may have two channels, or maybe more channels actually, for different systems, but you represent them just as pixels. But in MIDI, you use like a vector graphic for pictures. You just say it is grand piano. And then if you have card which can actually know what grand piano is, it synthesizes output signal from this grand piano just using these instructions. Grand piano here, start here, end up here with this volume and this particular timbre or whatever. And because of that, of course, what is good is that similarly as object-oriented pictures versus digitalized and pixelized pictures, it is like a sketch. It takes much less memory to describe sound in such way. So that's good. It doesn't take too much hard disk space, etc. What is not so good is that you depend on your sound card, how well this grand piano actually, this instruction playing grand piano actually can be executed. And in our practical exercise, we actually will try to do this both to deal with pixelated sound or sampled sound, and also with MIDI sound like vector graphics to do and understand how these things go. So MIDI is used quite a lot on different kind of computer games, etc., where storage space for this is important. For example, if you do not want to waste too much of space of this pixelated sound with samples, you just save it as instructions for these sounds. And MIDI also allows you to go in lower level, like just say this frequency with this timbre, etc. So we will not go into these details. So that's what is used in computer games, etc. But when you want to be very precise and not dependent on this MIDI, then of course you cannot use. And MIDI, because of that, MIDI is usually used either if it's shipped and distributed, for example with computer games and things where small differences are not important, but size matters, size as a storage to save it in the file. But if this consistency is important, then you can't use. And of course it's used internally for editors, for sound producers, because if they know how exactly their sound card works, how exactly these MIDI instructions are performed on his or her computer, then of course these guys can store their creations in MIDI format, because it is easier to edit, easier to store, and etc. So now little bit before we go into practical exercise about Linux sound system. Sorry for you who are using Windows computers and Mac computers. I used Windows long time ago and my knowledge there is quite outdated, but I know you I know something about Linux, and because Linux is becoming more and more popular, because Microsoft, similarly to other companies, is switching their attention more and more to services somewhere in cloud, so they put less and less money in actual operating system. And for example, for Windows 11, one of big changes is that it has even better support for Linux subsystem in Microsoft Windows. So I think that my prediction will come true, that sooner or later Microsoft Windows will be just a graphical front end for Linux-based operating system. And if it will happen, then of course knowledge about Linux-based operating systems will help. So, and if you look on history, there are different kind of sound systems which have their internal access points, which are in jargon called API, from application programming interface, so how you access it and how you manage them. And oldest system is called Open Sound System. Then was ALSA. An Open Sound System is common denominator for all Unix-based systems, including BSD, including Linux, including MacOS, iOS, Sun Solaris workstations, and which is now become Open Solaris, etc. So this system, Open Sound System, is common system for all Unix-like systems. But then for Linux there are differences. Initially for Linux they developed a system called ALSA from Advanced Linux Sound Architecture, then Pulse Audio, and you may see and read something about Jack, which is Audio Connector Kit, and it is recursive abbreviation. This means Jack is Jack Audio Connection Kit, where Jack means Jack Audio Connection Kit forever. And where are differences? So Open Sound System is the oldest one, and it is inherited in Linux-based systems from original Unixes, like BSD Unix and other Unixes. And it was developed for graphical terminals. And just a reminder, what graphical terminal means is that you have real computer somewhere in big room, and that is actual computer, and here you have display and keyboard. And if this is graphical display and it has also input for sound, then voila, you have something like powerful workstation like Sun Solaris. But what is important here is that for this graphical and sound terminal, actual processing is still happening here in this computer, and here it just sends data from keyboard, from mouse to computer, from microphone, and send data back. So this is very old standard, and probably you have heard that everything is a file in Unix-like system, and sound system is also a file. You may send random noise into this system, just reading from random device and redirecting its output into sound device. Or you can read from sound device and put it into file, and then you get it in WAV format, your digitalized sound from the microphone. Only problem is that it is very robust, works very well, only single access. So if you have computer game, only computer game will be able to produce sound. If you are listening some internet radio or whatever, only internet radio or whatever will be able to produce sound for you. So that is what is bad about this system. And modern Linuxes still support Open Sound System indirectly as a plugin or wrapper into Open Sound System. So if you have some very old application which can talk only to this Open Sound System approach, usually you can run this application by running this wrapper either of ALSA wrapper. You do something like OSSPD command or Pulse Audio DSP command, and so you can learn. Probably I will show you demonstration in practical exercise as well. So ALSA was leading standard around 5-10 years ago, and it was fork or difference from Unix based systems into Linux, and it solved this problem that you can access your hardware only from single process. So it introduced this mixing and different streams which you can use, for example, to produce some sound from one sound system to another. But for some reason, some of these guys didn't like it, and they introduced Pulse Audio as a more user-friendly system, particularly for mixing, etc. But what this Pulse Audio system actually is, it is front-end for user, which still uses this ALSA, an open sound system, as backend drivers. So Pulse Audio actually is something like front-end for management. And I do not know why they didn't choose to extend needed parts for this advanced Linux sound system, but they introduced Pulse Audio. And so most of modern systems are using Pulse Audio, but problem is that with Pulse Audio they are closed architectures and open architectures. For example, we have actually multi-layered architecture in Linux sound systems. Here is your hardware sound system, here maybe open sound system, maybe ALSA, and here Pulse Audio, and maybe Jack or whatever. And closed architecture is that if you add another intermediate layer here, you are allowed to access it only from here. So you actually do not know what is beneath this and how it actually works. But because of compatibility problems, etc., for all these additional architectural layers, there is still access allowed to connect to here, to connect to here, to connect to here. And that means you actually have big mess. You can manage something from Pulse Audio perspective, you can manage something from ALSA perspective, maybe you can even find some dusty corners where you can manage something from open sound system perspective, etc. So it's not closed architecture. So this is another layer which you mostly use, but for some reasons you may not use. For example, Pulse Audio controller is this upper layer where you can change different things for controlling volume, and it is poorly documented, but I can still open ALSA Mixer in this one, and then I am accessing this system not from Pulse Audio perspective, but from this older school perspective. And if I get some clashes here, that I still, and in most of cases if you use Pulse Audio you shouldn't use ALSA Mixer, but if you put some volume in ALSA Mixer to 0 and for some reason in Pulse Audio didn't catch these changes, then you get messed up with all your systems. And there was, but I think ALSA Mixer GUI is not, maybe it is installed. But I will not install, maybe again I will get some problems with my settings. And then for Pulse Audio, one of the problem is that it has large latency. It is not important when you are not doing it in real time. You are recording something, mixing, and then just rendering your data like movies. But if you need to do it in real time, then it's not good system, and therefore for many professional systems they use another IPI, another set of libraries called Jack, which has much lower latency. What is latency? Latency is time shift while signal is traveling through your system. And if you need to do it in real time, this timesheet should be very small, many microseconds, not more than a few milliseconds. But in Pulse Audio, for some of these you may get even hundreds of milliseconds. Okay, we will make a break and then maybe I will. So, and that's how it looks more or less in just general things in Linux-based systems. So you have different applications. For modern Linuxes, it mostly uses Pulse Audio as this management part. But for compatibility reasons and other things, you still may use OpenSonde system, you still may use ALS system, and then are your device drivers for particular Linux cards, and you have many Linux cards. For example, sound cards. I have one built-in sound card and I have one external USB card just to use it for my headphones, and it may actually get some problems. But okay, I have talked quite a lot. We can leave some of theoretical parts also for your practical exercise and demonstration. I think we need to do some break, but before we go to break, do you have some questions or comments? So now, before we go into your actual practical exercise, I think it is worth to explain a little bit more some of these technicalities. First, about these different sound systems on Linux. I, as a regular user, I try to avoid this jack system. Maybe if you get used to it and you know how to use it, it may be good enough. But I try to use these more standardized ones, and particularly for Pulse Audio, it is a problem that it is very poorly documented. For example, for Pulse Audio, if you go to their website and check this tool, Pulse Audio Volume Control, what it says is okay, I will prove it that it is. Here, documentation. There is not much to say. Just run it and try your best. Unfortunately, for some of Linux-based distributions, there is some little bit more documentation for this, but one of the biggest problems for Pulse Audio system is that it is not documented for error solution and how to use, etc. And there is one of Linux distribution called Arch Linux, which compiles many of tools and utilities from source code, and because when you need to do this, you need to know better. So actually, there are some of guides provided either for Advanced Linux Sound System or ALSA and Pulse Audio from this Linux distribution, which is actually much better than original Pulse Audio system distribution in their website. So why knowing about these systems is important? There are different kind of utilities and tools which still are actually using this old school Unix-like system, open sound system, to run. For example, there is sound synthesizer where you can add different kind of frequencies together in one in terminal. So you run it, and what you get is opening fsync input output error, opening DSP for output. What you need to know, what DSP is. I don't know what DSP is. I can only speculate that it's something like digital sound processor, blah blah blah. But what you definitely need to know is that DSP is this part of open sound system which is used to as a reference to actual sound card. And if you know this, and you know that your particular Linux distribution is using Pulse Audio, you can try to run this utility with a wrapper for Pulse Audio for open sound system. What it does, it allows for small amount of time direct access to actual sound card for this utility because of things because of protocol, how this open sound system interacts with actual thing. It needs to have exclusive access to this sound card, at least initially. But after that initial time, it actually creates fake virtual sound card which is added to actual sound cards through this mixer, so you can use this utility together with other without exclusive access. So if you know this, then you can try to run it with Pulse Audio DSP, and it still doesn't work, but because sometimes my sound card now is busy because of the Zoom session, because of used microphone, etc. So it is not 100% working all the time, because it actually may fail to get exclusive access for this initial amount of time. But if I try several times, so I got this working, and then what we can do, so here is wave sign. Let's make amplitude a little bit less. But it looks. So here it adds different kind of frequencies. And then you can use other utilities if they try to get this old school approach to your sound system using this open sound system protocol. So next one is about these pixelated or sampled sounds, and de facto standard in open source world is utility called or application called Audacity, and it is platform independent. You can run it in any Unix-like and Windows-based system. So you open it, and then here you have different kind of inputs, and again, don't be surprised because Audacity still uses ALSA standard to connect to your sound card. So here again, even though my top management layer for my Linux distribution is Pulse Audio, here I actually are using ALSA. Maybe if I use Pulse here, the proper ones here, it may work with pulse axis as well, but remember these are two different interfaces or two different protocols and ways how you can access your particular sound card. Oh, and you don't hear anything, that's bad. So, where was I? So, in open source world, if you want to use it for free and legally, then de facto standard for sampled audio files is a tool called Audacity. And before we go into a practical exercise, I will show you some important features of it. For example, about this sound analysis. Here I have prepared some tracks of it. All are mono tracks. And here are different kind of just sinusoids. And if I play it, and then you can analyze it. For example, plot spectrum for it. And here your resolution depends on how many samples you can use for this digital fast Fourier transformation from signal during time into frequencies. If these samples are too small, only thing you can see is that there is some signal around 400 Hz here. But if we increase these sample rates to higher and higher, we see more and more precisely that this signal is actually 110 Hz or A2 in musical notation. And so there is not enough data to use window size with 65,000 samples, so we see that in frequency spectrum this signal is like this. And similarly here we have much twice high frequency, here twice high again. And here we see beats happening in screen resolution because we have two rasters clashing together, my screen resolution with these sine waves, so it makes such a pattern. But if we make higher resolution, we see that it is still higher sinusoidal signal, and here it's even higher as well. And if we make them all together, we see something like this, and if we mix them, mix into new track. So here are all these signals together. And if we analyze this one, we see that here is 110 Hz of one of these components, then 220, 440, 880 and 1760. And you can analyze it also dynamically on screen in two different ways. In most of the times when you mix things, you are interested about amplitude of signal during time. But sometimes you may also be interested not in waveform, but in spectrogram. I don't know. Oh, that is just rendering glitch. So here you see that spectrogram is not changing. There is high amplitude. So here it's change of spectra during time. If you analyze it something like this, why does it show? Then it shows total amount of this spectrum from the start till the end of analyzed sample. But here it analyzes this sample with moving window during time. So dynamically it happens like this. We have some changing signal here, and then we are moving this window function around from time to time forward. And here we have the same problem as for quantum mechanics. If we create this window very large, then we can plot this spectrum very precisely. What are these components or frequencies during all this large window? But if this signal is actually gradually changing, it's not all the time from the start to beginning, these components will not represent signal precisely in each particular time. But if we decrease this size of window, then we can plot these spectrums, how exactly this spectrum looks like in this frame and that time in that frame. So we see how it's changing during time better. But of course we lose resolution here, because as smaller this window becomes, as more blurred these amplitudes become during because of a smaller window. So if we are more focused on changes, we can create this window smaller and see changes better, but the precision will be smaller. If signal is actually not changing much and we need more precision, we can create much larger window and see this more precisely. And here, I don't remember where these settings was. Spectrogram settings. So here we can say what is window size here. If we make it small, then it's very blurry. If we make it very large, it's much more precise, but of course we don't see any changes. And that is important, for example, for changing signal. So here are samples of different tones. Here is just sinusoid. Then here is so-called sawtooth. And here is chirp, which is called I don't remember. And if we analyze them, for example, we see here one very precise 440 Hz of amplitude. It is sinusoidal. So this was sawtooth signal, and we analyze spectrum for it, you see, because it has many sharp edges, and only limit for sharpness of these edges is sampling rate, because I cannot make it sharper than difference between two samples when this signal was sampled. In this case it's generated, not sampled, but we see that here are amplitude of very many different of changes. And here is another sharp signal, this meander or orthogonal changes. Again, we have much more components here, and here is Shannon signal, I don't remember. And we see here just everything. Why? Because here frequencies are actually changing during time, and if we look on spectrogram here, we see here that these three signals, sinusoid, sawtooth and bar, actually do not change during time. Here is only one component, here are several components, but they are not changing during time. But here in spectrogram you see that in this signal what is happening is that all these frequencies are changing during time and going up. And if you make it larger, it continuously goes up and goes up and goes up. And here, with this signal, you can actually test your melodic hearing. Because if you have good melodic hearing, it's not needed that you have absolute hearing, melodic is enough. You will base your hearing to some of these lowest frequencies, and you will hear that it goes up and up and up. But if you do not have good melodic hearing, you do not follow these changes, and then you just suddenly see that, oh, actually you can't hear this anymore, and your attention jumps from one of these amplitudes to this lower one, and then follows again. And for these people, they think that this pitch of this signal is actually going by jumps down and down and down and down. So if you follow one particular basic frequencies here and then just jump with your attention to next one, lower one here, you will say that it is going up. But if you will pay your attention to these jumps down and down and down and down, then you will think that this signal, pitch of this signal is going down. So that's what about this particular tool. And yeah, I think now we should be more or less prepared to look into your practical exercise. And this exercise consists of two parts. First is about MIDI. Okay. Then about MIDI editors. In MIDI editors, there are very many editors, particularly for Microsoft Windows, not so many for Linux. And long time ago, I used a cracked illegal editor called Cakewalk Studio, but now I try not to use cracked illegal systems, and One of editors you can use on Linux system is called Rose Garden. Problem with Rose Garden is that it is not a full package to use, because when I talked about these MIDI files, MIDI is just instruction, something like play G2 note with grand piano. It is like instruction draw triangle with this size, and drawing up this sound is up to other system or this MIDI synthesizer. MIDI synthesizers comes in two different parts, with so-called sound fonts and without. What is the font? Font is instruction to draw picture like this. Again, font is described as a object-oriented instruction part, so it do not describe all the pixels, but it describes some glyph or character as a set of curves. And so you can resize it, and actual pixels will be rendered accordingly to size and other things. And sound fonts is similar to character fonts. It is instruction what particular sound wave should be produced during time with this particular instruction. So that's why it's called fonts. It's similarly to fonts. You need to have instructions to produce actual pixels for these sounds waves to produce these sounds. And particularly for Linux, one of things what you can use as this sound font engine is called Fluid Synth. And you install this Fluid Synth and also Fluid sound fonts for GS, I do not know what it is. So you install this MIDI processor or this MIDI program which will follow these sound font instructions, and then you install it also for these sound fonts. And then you need to run it. And front end for it is, maybe I need to add. So here when you set up, you will see that it opens, but I will update this instruction. This is this sound processor which loads up these MIDI fonts. So in this case I'm using this MIDI fonts coming with this Fluid Synth synthesizer application or package. And again here, don't be surprised if audio driver is actually still ALSA or OS. So here you see all these different kind of interfaces which you may use. And again, as usual in Linux sound system, these are very poorly documented. Usually you end up just using try and error to check which one works and which doesn't work. I don't need to restart it. So this synthesizer will be actually producing my sound according to these MIDI instructions for MIDI editor. And so MIDI editor, which you can legally use for free, is called Rose Garden, and I think Rose Garden is also for Microsoft Windows. And if it's not, then you just check some of these and then you may share your experience with other ones. But again, tools are not important here because your homework is platform independent. You will need to provide just standardized file in MIDI format. So when I open this Rodigo, so do you still hear me? Because some of these editing tools may just reset sound card settings. So that means only Audacity is bad tool. And so here you need to make some notes, add some tracks here, edit it, let's say in Matrix Editor, put some notes here and play it. So, two large windows. Oops. How I play it. And so then you can save it, of course. But that is not what will be checked. What's that? What will be checked is that you will need to export it as a MIDI file. So save as or export, I don't remember. Export into MIDI file. And here you need to put your identifier. For me it was, I don't remember, but I have notes. So this is exercise number what? And looks like it crashed. I think again here problem is interaction with Zoom session, but let's check, did I actually get my file saved? Looks like not. Maybe it didn't like some extension or whatever. And here, let's rename it in separate way. And in Linux you can play it with another tool called Timidity. So that's probably what I will be using to check your completed tasks. And now about details. To pass this particular exercise, you need to put required notes there. If you have some musical education, you may make variations about it, like BACH, variations for Bach. But, example, everybody of us, so in this letter notation, all notes are starting from A till to H, and H actually is not mandatory, it is redundant. And sometimes I think maybe Bach introduced this note just to make variations about Bach theme. And at least some of these notes should be available in your name and surname. And so for me, I should put A and D notes in my project. And for beginners, matrix editor is probably easier, so A is, I think, this one. How can we check it? Well, I think, and then D actually should be. Oh, we delete it. Okay. And then you need to have at least 4 bars for this. I don't know how it will go. Right. And then we need to put another bracket to make our life more complicated. Not in this editor, that's for professionals. So these should be 2 octaves lower. It goes to that track. It should be correct one. So I'm not very professional user of this editor. I think I have somehow selected that as it. And I think that is minimum amount of effort you need to put it. So save your project in internal format, but to get credit, you actually need to export it as a MIDI file. And if you have fun doing this, then of course you can extend this minimum required amount of these notes to something more interesting. So that's about first part. Any questions, comments on this? I take that as no. Now about second part. Second part is about these bitmap oriented or sampled files, what I started to show you. You use Audacity tool or something better if you know. And first you need to record something. Good thing. We will test. Let's do it in the following way. If something crashes, we will at least have our recording. Actually, if it works and it's set up properly, we can actually, because I'm using microphone, we can use Audacity as a recording tool as well. Let's make new project. Hello, my name is Valdis. That will be enough. So, and if this recording doesn't work for you properly, then of course your default settings for Audacity are wrong. So then you need to check, for example, what kind of interfaces you have here, and you see here, because it allows me to access the same devices. First, I have two different microphones. I have three different microphones: built-in microphone, dedicated USB microphone, and microphone for external USB card. So these are three different devices, and it supports three different protocols: Pulse Audio, ALSA, and maybe even Open Sound System. And because of this, you will have 3x3 plus some more settings like left channel, right channel, and I have a big mess here for all these devices. Fortunately, probably for you, you will have only one microphone, so this list here will be much shorter, but still, if you need to go through all of them one by one, and then sometimes your sound system may get confused, you need to restart your computer, so these tests may take time. So you can use any editor, you can do some recording, but requirement is it's not easy to check that you actually record something using microphone, not just some already prepared external file like legal or illegal music or whatever. And then you need to export it to standardized formats. Again, actual editor is up to you, because what you need to prepare is an uncompressed FLAC format. So one channel, 444,106, blah blah blah. And if I check my default settings, this is at 16 bits PCM. I think I can just export it into FLAC format and it should be proper one with my default settings. Where can I see? Uncompressed files, FLAC files. Of course it should be FLACs, not WAV. So this is not important. And then, hello, my name is Valdis. And then how I will check metadata. Of course you can open with any editor you like. Hello, my name. And then you can go to the codec settings and check it. FLAC format, audio mono, 32 bits. I need 16. That's interesting how I will change it. This is project rate. So To check actual format more properly, I will use command line tool because it's much easier. Otherwise, I need to interrupt it somewhere in the middle to see it. It's quite hard. So what I will be using is command like soxy, and the actual file is not in this folder, but in this folder. And I will trust this tool, and if it says it's 16-bit FLAC as I exported here, I will trust it, not to 32-bit, what VLC player told to me. And here also, to prove your editing skills, it will be checked that this sample is precisely 1 minute long. So here in duration there should be 00, 01, and if there will be some fractions of seconds here, I will accept that, because you may get around plus minus 1 sample here. But if you edit it very precisely, because sample rate is high enough that you actually can cut off it precisely at 1 minute. And other format is another de facto standard. It is WAV file standard, but here we need to change it to lower bitrate and lower precision. And in theory you can do it also in exporting, but I don't know how to do it. I will actually change entire rate for entire project here, and then I will export this audio into where was I? Export audio other. So Microsoft unsign it 8-bit PCM. That I think is correct for me. So something right will come from project settings here. If maybe I needed to close it and open again, and actual bit depth will come from these exporting settings. Of course, if you use different tool, or Audacity may have many different import-export plugins, you can manage it a little bit differently. And how did I save it? Probably this one. And except it's too short, it looks good to me. Hello, my name is Valdis. When you hear here two different things. First, hello, my name is Valdis. Here I have high resolution, high sampling rate, and high resolution for numbers. Hello, my name is Valdis. And here it's much cleaner, but here I have two kinds of noise here. First, resolution is not high because frequency is very low, so it is phone frequency, phone quality, and also bit depth is low. It also has the so-called digitalization noise, because approximation of these numbers is not good enough that we hear it. Hello, my name is Valdis. Is very, that will be enough, low. And this particular format, for example, if you listen different kind of music, you probably one of digital effects what they are using is phone conversations, that somebody is talking through the phone, and to emulate this phone conversation you actually need to digitalize with sample rate 8000 Hz and 8-bit unsigned numbers. And mobile phones particularly add a noise filter to filter out this digitalization. For example, if we create new record and import audio with this WAV file, for mobile phones which are smarter than landline phones, what is actually happening here?
Hello, my name is
It adds this rendering error, or you see this digitalization numbers here. It's not very precise because with 8 bits it is quite. So we do effects, something about noise reduction. For example, we need to teach it. There is some silence. Let's say this is silence. Too short. So this also should be noise.
Hello, my name is Valdis.
Something like this. So that's how our mobile phones and landline phones actually transmit our voice conversations. So that is about second part of this exercise. And then of course you upload these files into my website. Any questions or comments on that? I take that as no. So next week, hopefully, we will continue as usual. And for those of you who will also want to attend this competing lecture at the same time, then I hope that you will be able to rely on recordings of these meetings, so you will be able to listen them in other time. Only then, of course, you may have some more problems with conversation. Then my proposal is to use email as a asynchronous way to interact with me. So if you have some additional questions, then I will try to answer by email. And usually when I get some additional questions, I also update these tasks with some known error solutions and workarounds, etc. And I hope that you will be able to do this with any operating system, because all of these outputs of files are just standardized file formats which you can produce with any tool of your choice. So, because we didn't have a very long break in between, I think that with that we can think that this session is done. So, thank you very much, and we'll meet next week, or we'll meet with next recorded session again. Bye.